Hello and welcome to the Chemistry Academy. In this video we're going to go over isomers in relation to the Advanced Higher Chemistry course. So you would have learned about isomers at National 5 and then built upon that knowledge a bit in higher. When you looked at isomers at National 5 and higher, you would have looked at what we call structural isomers. So these are the molecules that have the same molecular formula but they have a different structure, so the atoms are arranged in a different form. For example, butanol and butanone. So they're both made up of the same number of carbon, hydrogens and oxygen atoms, but the way that those atoms are arranged within the molecule are different. Butanol is classed as an aldehyde and butanone is classed as a ketone. I've drawn them in skeletal structure here because you want to try and get used to seeing molecules in skeletal structure now that you're doing advanced higher chemistry. So you can see here the carbonyl group on the end of the chain of 1, 2, 3, 4 carbons, telling you that it's an aldehyde with 4 carbons, giving it the name butanol. Here we can see there's a chain of 1, 2, 3, 4 carbons, again giving you a but, with a carbonyl group in the middle of the carbon chain, making it butan 2-one, or just butanone, because it can only go on carbon 2 if it's in the middle. So that's the isomers you'd looked at already, the structural ones where the atoms are arranged in different orders. In advanced higher, we then go on to look at stereoisomers. So stereoisomers are structurally the same, they have the same arrangement of atoms, but in space, 3D space, they are different. So there's 2 different types of stereoisomers. You get geometric isomers, so these are your cis and trans isomers, and we'll talk a bit more about that in a minute. So then we also get stereoisomers, which can also sometimes be called enantiomers. And these are non-superimposable mirror images of each other. So it's just kind of like your right hand and left hand. They're identical. They're made up of 1 palm and 4 fingers that are all kind of the same length, and then 1 thumb. And so they do look identical, but you can never place them exactly on top of each other. You can never make your left hand look and take up the exact same space as your right hand. So that's what you want to think of enantiomers or stereoisomers as like your right hand and left hand. These are 2 examples of stereoisomers here. This is a molecule called bromochlorofluoromethane, a bit of a mouthful. And there are 2 different enantiomers here, R and S. This is what we normally assign to the different enantiomers. One's an R and one's an S. This is not something you need to learn for advanced higher chemistry. You will maybe learn that if you go on to do chemistry at university level. But essentially you should be able to see here that they are a direct mirror reflection of each other. So it's hard to see when it's flat on the board, but if you were to rotate this molecule around and try and get it to fit exactly on top of here, you couldn't get it to be exactly the same. Okay, so you always want to think of the enantiomers as just mirror images of each other. If we talk a bit more about the geometric isomers before we go on to all of these, the 2 different types of stereoisomers in more detail. So we start with the geometric isomers. So geometric isomerism is not possible in every molecule. It's only possible in molecules that have both of these 2 things. So you first of all need a bond that has some restriction around its rotation. So that would be like a double carbon-to-carbon bond. They can't freely rotate. If you think about the double bonds kind of act as like a clamp and stops the carbons from rotating and twisting. Or if you have a cyclic ring. So that would be if you've got like a cyclopropane or something, or even something a bit bigger than that, you would get no free rotation, like those carbon single bonds couldn't rotate. So you're either looking for a double carbon-to-carbon bond in a molecule or some kind of ring formation. And the other requirement that you then also need on top of that is that both ends of the molecule, or each carbon in the restricted bond, has 2 different substituents or groups attached to it. So the example for this one here would, if this is my restricted bond, we could have each one with a hydrogen and then also maybe like a chlorine. Okay, so that would be each carbon involved in the restricted bond has got 2 different substituents attached to it. If we look at the geometric isomers, I've got down here, you can see that again, there's a double carbon to carbon bond, so there's restricted free rotation, and then each of the carbons in the double bond have two different groups attached to it. So it's got a methyl group and a hydrogen on each side. This then means that because they can't rotate, the bond can't rotate, it means if you switch the groups on one side, you've essentially made a different geometric isomer, because now that molecule's taking up a different arrangement in space. So the two examples I've got here are where the two methyl groups are pointing out of the board, and in this instance here, there's a methyl group pointing out and one pointing back into the board. So that's a different spatial arrangement, which is why they are two different geometric isomers. A geometric isomer of this molecule here, if I just pop it down here, would be if we have the same ring, but like I said, we flip the groups on one side. So we would have this time, instead of the chlorine going forward, it would go back and the hydrogen would point out the way. So they are two geometric isomers as well. When we're assigning geometric isomers, we call them cis and trans. Cis means that the two groups are on the same groups are on the same side. So here you can see the two methyl groups are on the same side of the double bonded carbon bond. Our cis isomer from this one here would be this one, because the chlorine groups are on the same side. Trans means opposite sides. So here you can see the methyl groups are pointing in different directions. One's on this side, the other's on the other side. And this would be our trans isomer for this molecule here, because the chlorines are on different sides of the molecule, or opposite sides. So try and remember cis, same. The other thing that's useful when it comes to cis and trans is if it's drawn in a skeletal structure, the cis will be in a C shape, so you should be able to see a C shape in the molecule. The trans is more like a Z shape, so I often imagine like if that S was a Z, like trans, that reminds me it should look like a Z if it's a trans isomer. Okay, so it's important that you can identify if it's cis and trans, and just remember that cis means this groups or the substituents or same substituents are on the same side, and in trans the same substituents are on opposite sides. But the two requirements are that you need a bond which has restricted rotation, so that's either your double carbon to carbon bond or a cyclic carbon ring, and then the carbons at each end of that restricted bond need to have two different substituents on them. Okay, so that's your geometric isomers. So then if we go back to our enantiomers or your optical isomers, these again don't occur in every molecule. It only happens in molecules that have a chiral carbon centre. So a chiral carbon centre is where you have four different groups attached to a central atom. So for example here, let's show this one down here, this carbon here is attached to four different groups. It's got a fluorine, a bromine, a chlorine and a hydrogen, four different things. So that would be a chiral carbon centre. Oops, dropped my pen. Quite often you're asked to identify these in an exam, the chiral centres, so that would be our chiral centre here. You can also get asked to identify a chiral carbon centre within a bigger molecule, like this one here. So again, you're looking for a carbon that's got four different things attached to it, so it's never going to be a carbon that's made a double bond or anything. It needs to be an sp3 hybridised carbon. So we've got all sp3 hybridised carbons here, but this one has got 3 hydrogens on it, so that's not that doesn't have 4 different groups. This carbon here has got 2 hydrogens on it, so again, not 4 different groups. This carbon here has got hydrogen, and this is where people get confused because they think, oh well, that's a CH2 and that's a CH2, so that's two of the same thing. But when we talk about different groups, you need to think of the whole thing that's on the other side of that carbon. So that would be the group there, and that would be the group there, and then that would be the group, and then that would be the group. So because that does have 4 different groups around it, that is a chiral carbon centre there. This one here is not, because it's got 2 hydrogens attached to it. So just watch out for that in the larger molecules. the whole other rest of the part of the molecule on that side is what's classed as the group. And if that's different to what's on that, then it is a chiral carbon center. Okay, that means that you could have the R or the S rotation around, or arrangement around this carbon center. So you might have this going back, this coming forward, and this being flat and this being flat, or you could rotate it around where that's coming out and then that one's going back. So you don't often get asked to draw optical isomer or enantiomer arrangements for larger molecules. It is usually for this one, but my advice would be is to take the wedged and hash bonds and just swap them around. Or if you can draw a complete mirror image, then that does make it a bit easier, but if in doubt, just take the wedged and hashed bonded substituents and swap them over, and then that gives you a different enantiomer. It's hard to see it here because of the way it's arranged, but if we were to take the bromine across this side, it would, in space, 3D space, it would end up being a different thing. The thing about the optical isomers or the enantiomers is that they are identical except for the way, well, in all their physical properties and chemical properties. So like their melting points are the same, their boiling points are the same, their solubility is the same. The only difference, or the way you can tell them apart, is that they affect light, plane polarized light differently. So they are classed as being optically active. They do rotate plane polarized light, and they'll rotate it by a given angle in the opposite direction. So say this R enantiomer rotates it by plus 30 degrees. This one would rotate it by minus 30 degrees. So it's the equivalent, same equivalent numerical angle, but in the opposite planes or opposite directions. A mixture of enantiomers that is optically inactive, where there's no overall rotation of the plane polarized light, that's known as a racemic mixture. And the reason it's not optically active and doesn't actually have an overall effect on the plane polarized light is because you've got equal concentrations of both enantiomers. So the polarization of the light essentially cancels out. Because let's say you've got half a mole of this rotating at plus 30, and then there's half a mole of this rotating it by minus 30, then you've got a net of 0 degrees of rotation because you've got the same amount plus as the same amount minus, so it will cancel out. If you don't have a 50-50 ratio, the polarization will depend on what you've got in excess of. So let's say we had 25 centimeters cubed this one and 75 centimeters cubed of this one. And so basically whatever rotation is caused by 50 centimeters cubed of this is going to be the rotation you see on the light, because that's what you've got in excess. You've got 50 centimeters cubed more of this than of this one. So sometimes you're given numbers in the exam where you've got to calculate an overall rotation of the light, and it is just to do with the proportions of the enantiomers that you have. So just look to see which enantiomer you've got in excess, and then there should be enough information there for you to work out then therefore how much rotation will actually be perceived. Okay, and that's it really. So hopefully you found that useful to help you get your head around isomers. And so we've got the geometric isomers and the optical isomers. And yeah, just don't forget about the racemic mixture, because that comes up quite a lot. So it's where you've got equal proportions of both enantiomers and it is optically inactive. If you found this video helpful, please give it a like. Don't forget to subscribe, and I'll see you again soon.